Welcome everyone, and thank you for joining us today's CCS talk session. The topic is the value of CCS. Earlier today, we also published our most recent thought leadership report with the same title. It's on our website and it's free and available for everyone to download. I want to say that our CCS Talks webinar series have been getting a lot of traction recently in the past few weeks, but today's session received a record number of registrations, more than 1,000, clearly showing a huge interest in the topic. So again, once again, thank you very much for your interest and your participation today. My name is Galoran Turan, and I'm the General Manager of Advocacy and Communications at the Global CCS Institute. The Institute is an international think tank whose mission is to accelerate the deployment of CCS as an essential climate mitigation technology. Our headquarters are in Melbourne, Australia, and we have presence in 5 other countries, including China, Japan, Belgium, the UK, and the US. Before we actually start the discussion, the webinar, I would like to say a few words of housekeeping. You will see a bar at the top of your screen, and if you click Everyone button, you'll be able to see all the 2 presenters and myself, as well as the slides, all at the same time. Today's webinar will be roughly an hour long. During the first 40 or 45 minutes, Alex and Nabil, our presenters, will be discussing the report, and during the final 10, 15, 20 minutes, we'll be taking and responding to questions. So I encourage you to ask questions throughout the webinar, and you can do that by using the GoToWebinar panel that you see on your computer. Finally, a recording of this webinar and the slides will be made available after the webinar. It's going to be on our website, and in the coming days you will receive an email with a link to the recording. Today I'm very pleased to be joined by the authors of our report, The Value of CCS, Mr. Alex Townsend and Ms. Nabila Raji. Alex is a senior economics consultant with us, and prior to joining the Institute, he was working for the UK government for close to a decade. Nabila similarly has worked for governments, actually both Australia and Sri Lankan governments, as well as the non-profit sector. And today Alex is joining us from London, and Nabila is joining us from Melbourne. With that, I would like to turn to Alex and ask him, Alex, could you please introduce us to this report? What is it about, the value of CCS?
Yeah, thanks, Galoran. So the report summarises recent analysis, including by the Institute, on the benefits of CCS deployment. And the report discusses the benefits under 2 overarching themes. The first theme covers the value CCS provides as an essential climate mitigation tool that will be needed if we're to reach net zero emissions by the middle of the century. And the second theme covers the broader benefits the deployment of CCS provides in terms of clean growth opportunities, creating and retaining jobs, and helping to ensure a just and sustainable transition.
Thank you. So you started by saying it's a essential climate mitigation tool. Can you elaborate a little bit more about it and provide detail as to why and how you think that is the case?
Yes, so in the report we approach this from 2 different perspectives, a global level perspective and a sector level perspective. I'll talk through the global level perspective, and then Nabila and I will jointly run through the sector level perspective. So at the global level, analysis by the IPCC and the IEA consistently shows CCS playing a major role in meeting long-term climate targets. So for example, the IEA Sustainable Development Scenario, which is consistent with meeting the goals of the Paris Agreement, shows that 2.8 gigatons of CO2 would be captured and stored using CCS in 2050. And to put that into context, global emissions of CO2 today are around 35 gigatons a year. And excluding CCS from the list of technologies used to meet climate targets has been shown to increase costs. So for example, in the IPCC's 5th assessment report, excluding CCS from the suite of technologies available to meet a 2-degree target was shown to lead to a doubling in the costs overall. And that's partly because there are several low-cost applications of CCS, such as natural gas processing, fertilizer production, and ethanol production, where the cost of capture is relatively low and is cost effective under relatively low CO2 prices. And as well as being part of the lowest cost pathway to meeting climate targets, investing in CCS also helps to reduce the risks of meeting those targets. And that's for a few different reasons. So firstly, as I mentioned, there are several low-cost applications of CCS, which it makes sense to deploy in any low-risk, low-regret strategy to address the challenges of climate change. Secondly, deploying a portfolio of technologies, including CCS, helps to diversify away some of the risks. And thirdly, investing in the low-cost CCS applications today provides the option to deploy it in higher cost applications in the future where there may be limited alternatives available. And we illustrate this in the report using an example from the UK and the Committee on Climate Change's advice to the UK government on reaching net zero emissions. So in their net zero report, the CCC identified 3 options as shown in this chart. You have core options that make sense under most pathways to get the UK to an 80% reduction in emissions by 2050 relative to 1990. Further ambition options that, when added to the core options, get the UK most of the way to net zero. And then what they call speculative options that would be required to reach net zero. And as you can see in this chart, in this slide, CCS features across all of these options. And crucially, without investment in CCS today, in the low regret core options, the opportunity to deploy it in other applications, such as those in the speculative options, will be limited. So ultimately, this could result in climate targets not being met, or only doing so at a high cost. And the focus on some of the sector level applications of CCS in the UK example provides a useful segue to the second perspective we take in the report, where we look at the sector level perspective on the value CCS provides as a climate mitigation technology. And in there we consider 4 areas in particular where CCS is likely to play an essential role. So they are achieving deep decarbonisation in industry, providing low carbon dispatchable power, enabling the production of low carbon hydrogen at scale, and delivering negative emissions. And the next slide, a few slides, will provide a bit more detail on each of those. So starting with the first area, achieving deep decarbonisation in industry, overall industry accounts for around about 40% of global energy demand and a quarter of global CO2 emissions. So reducing emissions in industry, and in particular the cement, chemicals and iron and steel sectors, as you can see in this chart, which account for a large proportion of industry emissions, is critical to meeting long-term targets and reaching net zero emissions. However, there are 2 major challenges with reducing emissions from industry. Firstly, as you can see on the right-hand side, 1/4 of industry emissions are process emissions that cannot be avoided by switching to alternative fuels. So, for example, in cement production, around 65% of emissions are associated with the calcination of limestone, which is a chemical process underlying the cement production. And secondly, as you can see on the right-hand side, 1/3 of the energy demand by industry is for high temperature heat. And switching from fossil fuels to alternative fuels for this heat is difficult and costly. Hydrogen is one option, and as we'll discuss later, CCS has a role to play in low carbon hydrogen as part of that solution. So the value of CCS from the sort of industry perspective is it's one of the most mature and cost-effective options for reducing emissions from processes by capturing CO2 directly, and reducing emissions from high temperature heat by capturing the emissions from the combustion of fossil fuels. And that's led many, including the IEA and the Energy Transition Commission, to conclude that achieving deep emissions in industry without CCS may be impossible and at best more expensive. If we jump on to hydrogen, and then perhaps we can come back to power once Navila's got sound back.
Okay.
So the next area we looked at within the report is the production of low carbon hydrogen at scale. So hydrogen is likely to play a major role in the decarbonisation of hard to abate sectors, as I mentioned earlier. And it could also be an important source of energy for residential heat demand and flexible power generation. And that's led many to conclude that the global hydrogen production will need to increase several times over, from around 70 million tonnes of hydrogen produced a year today to 400 to 650 million tonnes by 2050. And that hydrogen will need to be low carbon, and there are three main technologies available that could be used to scale up the production of low carbon hydrogen. And they are gas reforming with CCS, coal gasification with CCS, and electrolysis powered by renewables. And each of these technologies has its own benefits and will have a role to play in scaling up the production of low carbon hydrogen. And the advantages of hydrogen production with CCS centre around its maturity, its scale, and its commercial viability. So large-scale hydrogen production facilities with CCS have been in operation for almost 2 decades, and there are currently 5 large-scale CCS facilities in operation at plants that produce hydrogen, and 3 under construction. So it's a relatively mature technology that has been proven at scale. And then on commercial viability, hydrogen produced using coal or methane with CCS is currently one of the lowest cost options for producing low carbon hydrogen, with costs of around $1.5 to $2.5 per kilogram, compared to $4 to $7.5 per kilogram for hydrogen produced using electrolysis. And we expect the cost of electrolysis to fall significantly in the future, but hydrogen production with CCS will remain a commercially viable option in the near term, and in particular in the longer term in those places where low cost, large scale renewable resources are not available and fossil fuel prices are low. So we'll just switch back, Navila, to the power section for you to cover that one off.
Is it possible to hear me now?
Yes, it is.
Yeah, sorry about that, everybody. So the second area that we have highlighted in the report that CCS provides as a benefit is providing low carbon, dispatchable and reliable electricity. The power generation sector accounts for the largest emissions globally, and if we are to achieve net zero emissions in the near future, by 2050 at least, we will need rapid decarbonization. And right now, the renewables are heading the transition to a low carbon electricity grid. And in the report, we highlight how CCS equipped with conventional fossil fuel power plants play a complementary role within this context. This is because a low carbon electricity grid must not only make sure that supply matches demand, but also that the electricity supplied is stable and reliable, as you can see in this diagram. So the nature and physical configurations of CCS equipped power plants is such that they're able to provide power as needed in response to demand, which is known as dispatchability. And they're also able to provide ancillary services like inertia and frequency control, which are essential for maintaining the stability and the reliability of the electricity supply. Renewables provide low carbon and affordable electricity, but on the other hand, the intermittency of these sources of technology make them unable to adjust electricity supply based on demand, and also provide ancillary services like frequency and voltage control. So the value of CCS equipped power plants comes into play here, because it is inevitable that renewables will need to be complemented by dispatchable sources of sources like CCS equipped plants to maintain the reliability of the grid. And we also highlight in the report that given this unique value of CCS, that it is inadequate then to only take into account the cost of generation when making decisions about the optimal technology mix for the future electricity system. Because these decisions will need holistic evaluation metrics, which assess the impact of the technology on the cost of managing the whole electricity system. And studies that utilize these metrics from a whole systems perspective have shown that, or when they assess different technologies, have shown that the ability of CCS-equipped power plants and their ability to provide low-carbon dispatchable electricity and ancillary services makes it a competitive option, which complements the deployment of other low-carbon sources of electricity, for example, like renewables. Over to you, Alex.
We'll skip through this one again, and back to you, Nabila.
Oh, yeah, okay. So again, the fourth area that we explored in the report, which CCS plays a role in delivering a benefit, is by delivering negative emissions. Achieving negative emissions through the removal of CO2 from the atmosphere will be required if we are to address the challenge of residual emissions in hard-to-abate sectors. CCS provides the underlying basis for two types of negative emissions technologies that we have identified in our report. The first being bioenergy with carbon capture and storage, BECCS, and also the second type being direct air capture technologies, which are also called DACS technologies. And there are a number of examples of BECCS technologies operating today, and the most notable of them being the Illinois CCS industrial facility in the US, which captures 1 million tons of CO2 a year from producing ethanol from corn. And DAC technologies, on the other hand, which use chemicals to directly capture CO2 from the air, are less mature in comparison to BECCS. However, there are still notable examples in operation today, like those developed by Climeworks, Carbon Engineering, and Global Thermostat. We discuss in our report that even though these technologies are attractive options for mitigating and delivering negative emissions, they're not without their challenges. For example, scaling up BECCS, there are concerns revolving around land availability for energy conservation, energy crops, as well as supply chains of sustainable biomass. In the case of DACS, the concerns revolve around costs as well as high energy intensity in order to pull a low concentration of CO2 from the air. Having said that, in our report, we highlight how in achieving net zero emissions without these technologies is considered a mountainous and challenging task, even if it may be theoretically feasible. And with every year that passes without significant CO2 reductions, the importance of negative emissions to achieve Paris Agreement targets is also clear. Since CCS is the foundation for these two negative emissions technologies, we can see that it is crucial for achieving net zero emissions.
Thank you very much both for addressing the climate benefits of CCS, in particular the different industries from, as we discussed, direct air capture, negative emissions, to hydrogen, to power, etc. Given the current economic circumstances we're facing globally, what are some of the sort of broader and more, let's say, mainstream economic benefits of CCS? If you could kind of talk a little bit about those as well, please.
Yeah, so there are several broader benefits from the deployment of CCS, and in the report we focus on four in particular, which are listed on this slide. So the deployment of CCS creates and supports jobs, supports economic growth through new net zero industries, extends the lifetime of infrastructure and defers decommissioning costs, and facilitates a just transition. So Nabila and I will run through each of these in the next few slides. So the deployment of CCS creates and supports jobs, and these employment effects can be broadly separated into three areas. So firstly, CCS creates jobs in the construction and operation of facilities, CCS facilities. Secondly, it safeguards jobs at the industrial plant where the CCS facility is located. And thirdly, it also supports jobs in the wider supply chain, both the CCS supply chain and that of the industrial plant where it is located. And I'll run through the evidence that we cover in the report in the next couple of slides on that. So firstly, as large infrastructure projects, the construction of CCS facilities requires a large number of workers. So for example, for the Boundary Dam project in Canada, 1,700 people were employed at the site during peak construction. And similarly, for the Alberta Carbon Trunk Line project in Canada, around 2,000 people were employed during peak construction. The operation of CCS facilities, on the other hand, tends to require a relatively small number of workers. So, for example, based on data we've collected from projects currently in operation, around 20 people on average are employed at a typical capture plant. And I guess some on this webinar will be aware that we often talk about needing at least 2,000 large-scale CCS facilities by 2050 if we are to keep on track with the goals of the Paris Agreement. And so reaching that level would require a build-out rate of around 70 to 100 facilities per year. And so if we were to scale up the estimates I just mentioned and apply some relatively conservative assumptions, then that would suggest that at least 100,000 people globally would be needed in the CCS construction and operation industry by 2050. And actually several studies suggest that that could be several times larger. I think with that being said, putting it within the context of other industries, say for example the iron and steel industry where 6 million people are employed, it's relatively modest. But you know, critically, those are important employment opportunities for the from a kind of local perspective for the region that they're based in. In addition to creating jobs in the construction and operation of CCS plants, CCS also supports employment at the industrial site where it's located, and this is perhaps where the largest employment opportunity lies. So in the absence of CCS, as we've mentioned above, some of the plants will have to close down in order to meet climate change commitments. So by enabling the likes of the cement industry, the chemicals industry, and the iron and steel industry to transition to a net zero economy, CCS enables them to make a sustained contribution to the local economies where they're based. And there are three characteristics we highlight in the report that make these industries particularly valuable to the communities and regions they are located in. So the first is they're large local employers. So for example, a typical integrated cement plant might employ 200 to 400 employees, a refinery around 1,000 employees, and an integrated steel mill nearly 2,000 employees. So individual plants can account for a relatively large proportion of the workforce in a given area. Secondly, these industries tend to be co-located in clusters in close proximity to ports and other infrastructure, and with access to suppliers, clients, and the skilled workforce. And these clusters are important regional hubs for employment and amplify the importance of individual plants to a region. And finally, these industries provide well-paid jobs. And we illustrate this in the report with analysis of the wage premium in these industries for the US and the UK. And in the slide here, you can see the example for the US. So the chart shows the distribution of wages in the US in the industries listed relative to the average wage in the state they're located. So for example, if you take refineries, we've compared the wages in refineries in Texas, say, with the average wage across all jobs in Texas, and then replicated this analysis for all states, and then plotted the distribution in this chart. So you can see here that all of these industries pay above average wages, as indicated by the distribution being skewed to the right-hand side of the chart and above zero. So the combination of being large local employers, being co-located, and providing high-paid employment means that these industries are viewed as high-value industries to the regions that they're located. And by enabling them to transition to a net zero economy, CCS helps to protect employment in these industries and the regions that are dependent on them. And then the final area we talk about in the report is that as well as these direct jobs created in the construction and operation of CCS facilities and at the industrial plant where it is located, CCS can support jobs indirectly in the supply chain. And relative to other sectors, CCS-related supply chain multipliers are quite high. So, for example, in the UK, the refinery, cements, petrochemicals, and iron and steel industries all rank within the top 30% of employment multipliers. And these are the industries which are most likely to be providing the goods for CCS facilities, for the production and construction of CCS facilities, and also the location of most of the CCS facilities, as we've alluded to earlier. And some studies take these employment multipliers and then use them to effectively estimate the sort of total gross employment effects of large-scale CCS deployment. And so one example is a recent report published by SINTEF, a Norwegian research agency, who estimate CCS deployment could support up to 150,000 jobs in Europe, of which 60 to 70,000 would be in the supply chain. So whilst it's difficult to gauge the additionality of these jobs, they nevertheless show that the employment effects associated with the deployment of CCS can go beyond just the industrial plant itself and the construction and operation of the CCS facility.
So a further benefit that's provided by CCS deployment is that it will create new opportunities in a range of markets, for example, for low carbon hydrogen, negative emissions technologies, as well as other CCS applications. To get an idea of the size of the market that could be involved, the Hydrogen Council has estimated that in 2050, the global hydrogen economy could account for 18% of final energy demand, which amounts to about $2.5 trillion and an employment for about 30 million people. And when you look at Europe, the market could reach 820 billion euros, or an employment for about 5.4 million people. So you can see that these industries could become some of the high-value industries of future economies, providing a new employment and business opportunities. And the prospect of growth in these markets will stimulate innovation as companies compete for market share. So the innovation will lead to improved productivity, which in turn generates economic growth. And the value of innovation has increasingly been the focus of research, given its role in supporting economic growth. So there's some emerging evidence that suggests that new CCS-related markets could be the source of innovation-led growth and high-value innovation spillovers. And in the report, we provide a summary of research that was published by the Grantham Institute of the London School of Economics, as well as Imperial College, that ranks technologies based on the value generated through innovation in these technologies. And they estimate innovation spillovers based on data of 1 million patents globally, estimating spillovers based on the number of times a patent has been referred in a future patent. And looking across a wide range of sectors, they find that CCS is a source of high-value spillovers, as shown in the chart. For example, in the UK, the value of a patent in terms of spillovers it provides is around 50% higher than the average patent across the technologies considered. However, compared to other sectors, the volume of CCS innovations is relatively low. So, for example, in the UK, the number of innovations is 50% lower than average. That puts it similar in size to industries like geothermal and building efficiency innovations. And so this raises some interesting questions from a policymaker's perspective, but suggests that the development of some of the CCS-related industries could support economic growth.
Okay. The third opportunity then we highlight in the report is that the deployment of CCS can extend the lifetime of infrastructure, and in doing so can help to defer decommissioning costs. And just to explain that rationale in a bit more detail, where oil or gas production fields are at the end of their lives, there may be opportunities to reuse the existing oil and gas infrastructure by repurposing it for CO2 transport and storage. And this can reduce the cost of building transport and storage infrastructure, reduce permitting time, and it can also defer the costs of decommissioning infrastructure, which frees up resources that can be used and invested in other value-generating activities. Globally, the theoretical potential looks large, as you can see on the chart on the left-hand side here. So over the next decade, nearly $85 billion US dollars is forecast to be spent on decommissioning. And as you can see, the largest markets are anticipated to be the UK, followed by the US, Brazil, and Norway. Looking at it at an asset level, though, provides a slightly more nuanced view of the opportunity. So on the right-hand side, we've shown the breakdown in decommissioning costs by activity. And this is based on UK data, but the breakdown will vary by country and location, but generally you'd expect the ordering of the costs to be similar to what we've shown here. So at this asset level, pipelines provide perhaps the most promising prospect for reuse and deferring decommissioning costs. And to determine whether you can reuse a pipeline, full sort of integrity check needs to be carried out on the pipeline, and the operator in particular will be wanting to check for the risks around corrosion. But where it can be, where those risks are low, then there's the opportunity to reuse it for CO2 transport. However, as shown in the chart here, the decommissioning costs associated with subsea assets, which includes pipelines, is relatively small, so it's a relatively small proportion of the overall decommissioning costs. Other assets could potentially be reused, but there will be a range of technical, regulatory and commercial factors that need to be considered. So for example, oil and gas wells, which account for the largest proportion of decommissioning costs in terms of well decommissioning, they may be suitable for CO2 injection, but because of differences in design standards and operational requirements between oil and gas production wells and CO2 injection wells, it's likely that some remedial action will be needed to adapt the well equipment. So ultimately, in these cases, the operator will need to weigh up the additional costs of the remedial work and any other risks associated with using an older well, with the time and the cost savings of not needing to drill a new well. So in practice, what we see is that whether infrastructure is reused or can be reused will really vary on a case-by-case basis. But where there is that option, it provides the potential to reduce the cost of building the transport and storage infrastructure, reducing permitting time, and in doing so also deferring decommissioning costs.
And so also the CCS is an important tool in achieving a just transition, because the combination of creating new job opportunities as well as enabling existing high-value industries to make a sustained contribution to local economies places CCS in that position. One of the greatest challenges of achieving a just transition is that there's a mismatch between the geographical location and spread of job losses and gains and the timings of those changes as well. So the jobs created in low carbon industries may not necessarily occur at the same time that job losses happen in high emissions industries. And so one advantage of CCS is that it provides employment opportunities at the same time and place where they're most likely to be needed to support a just transition. In the report, we highlight several initiatives underway in different countries by governments to identify and plan for the impacts of the transition to a net zero emissions economy. And this is really great to see it moving up the agenda. However, to date, most of this activity centers around the phasing out of coal, and these initiatives will need to start thinking a lot more broadly. And some are about the sectors and regions affected. And so it's important when doing that that they appropriately reflect the role CCS can play in supporting a just transition.
Thank you both very much for this very detailed overview and analysis of both the climate and the broader economic benefits of CCS. So bringing this to a close, in a nutshell, kind of what conclusions should we draw from your report and your analysis? Alex, if I may start with you.
Yeah. So perhaps if I cover the sort of policy perspective, then Vida can talk a bit about the sort of research questions. I guess, so from a policy perspective, the report highlights the importance of taking into account the broader benefits of CCS when designing climate change mitigation strategies. And so that includes the role of CCS in reducing emissions in hard-to-abate sectors, in hydrogen and electricity production, and negative emissions. It also encompasses the role it plays both in terms of reducing the costs and the risks of meeting climate targets, and also the broader benefits it provides. And in particular, I think the benefit it provides is part of the solution to the just transition, as Nabila mentioned. And so taking these into account should ensure that CCS features more prominently in country level climate change mitigation strategies, and really it will need to if countries are serious about meeting net zero emissions commitments. Nabila, could you say something perhaps on the research side?
Yeah, so our report also highlights some areas where we can undertake further research in order to build an evidence base. And for example, the areas we've highlighted is on the cost of meeting 1.5 degrees pathways without CCS. Also, secondly, on the additionality of job impacts related to CCS. And also, we think another area is that on the value of CCS innovations itself, where the evidence is new and emerging. So improving the evidence database could help us to further bolster the case of CCS.
Okay, well, thank you very much both. And with that, I would like to open up for questions. And since the beginning of the webinar, there have been questions pouring in through the platform, the GoToWebinar platform. I just want to say I've been trying to keep track of them and categorizing them into themes and groupings, etc. And I'll start posing them to Alex and Nabila. But in case we run out of time and we don't get to your question during the webinar, I just want to mention that we've been collating the questions, and we will try to get back to you within the coming days with answers. If we don't get it to the during this webinar right here, right now, we will try to get back to you as much as we can, as much as it's feasible. With that, I would like to start by, so there have been a number of questions about the costs of CCS, and also there have been a number of questions around therefore corresponding the carbon level of carbon price, carbon tax that is needed to remunerate and make the business case for CCS. So could you talk a little bit about the costs, and particularly kind of, there was one question about who's expected to pay for this. So perhaps Alex, if you could help us with that.
Yeah, sure. So I guess, yeah, the purpose of the report was to highlight the evidence on the benefits of CCS, but of course we need to also consider that alongside the cost to get the full picture. And there isn't really a single estimate of the cost of CCS. It varies by industry and along the sort of CCS supply chain. So as I mentioned, there are some low-cost applications where the cost of capturing CO2 is very low, and that's because as part of those production processes, they provide a relatively pure stream of CO2 that it's low cost to capture. And then you have other applications where the purity of CO2 is lower, and therefore there's a higher cost of capture. So there's variety across industries. There's also variety in terms of transport and storage. So based on the distance, the mode of transport, whether it's offshore or onshore. So ultimately what you have is a spectrum of CO2 costs, with some relatively low cost applications like natural gas processing, ethanol production, fertilizer production, where you're looking at costs sort of below $25 per ton of CO2, to sort of some of the more higher cost applications. But I think from a climate mitigation perspective, ultimately what we're interested in is the cost of per ton of CO2 avoided. And when you look at it on that basis, and that metric, which these models do, that kind of look at it from a global perspective, you see sort of CCS featuring heavily because it's a cost-effective solution across many of these different industries that we've discussed. So I think that's probably that on the cost side. In terms of, I think you mentioned who pays. I guess that will depend partly on policy. So the policy framework will ultimately dictate kind of who ultimately pays for the cost of CCS. There have been a few studies that have looked at the impact on the cost of final products. So, for example, how much does CCS add to the cost of concrete and cement used in the building of a house, or to the cost of steel used in production of a car? And I think they tend to show that the cost impacts are relatively small, and so are manageable.
Thanks, Alex. Number of questions about negative emission technologies, and particularly about noted direct air capture, costs of direct air capture, what are they expected to be, etc. Nabila, maybe if you could kind of talk a little bit about negative emission technologies, and particularly with direct air capture, how do you see that playing out? And given the commercial viability issues that you mentioned, are there other kind of options that should be considered potentially?
Thanks, Lauren. Good question. We talked about during the discussion about the role of negative emissions towards achieving Paris Agreement targets. With each year that goes by without significant CO2 emissions reductions, that reliance on negative emissions is even more increased. And this is highlighted even in the IPCC 1.5 degrees report, a special report, which says that it's not enough that we do not emit as well. It's also that we need to remove residual emissions, especially that is coming up hard to abate sectors. And in terms of the commercial viability, like we did discuss the challenges around cost as well. Costs of DAC technologies has been right now is estimated to be between $600 to $1,000 per ton of CO2 captured for first of a kind projects, and this is considered quite expensive. And even though costs are expected to fall within as the technology develops, research suggests that costs will still remain between around $100 to around $300 per ton of CO2 when deployed at scale. However, given this reality though, and the reliance at negative emissions technologies, going about a means to achieve net zero using other means has been shown to be almost infeasible. For example, if you take again the IPCC 1.5 degrees special report, and they have 4 illustrative pathways in which the globe can proceed towards achieving 1.5 degrees by 2050, and it shows that temperature rises. There's one pathway where they explore the possibility of temperature rises being limited to 1.5 degrees without CCS or without negative emissions technologies like BECCS and DACs. And so if that is the case, it requires a drop of 5% per year in energy intensity levels between now and 2040. And when you compare that reality with the fact that since the 1990s, energy intensity has been dropping by only about 1.6% every year, you can see that achieving that sort of without CCS as negative.
Sorry. Whilst you were sort of talking, this question just came about. When you sort of said 600 to 1,000 in terms of the negative emissions, is it direct air capture or is it BECCS included? I believe that's only direct air capture, right?
Yes, that is only direct air capture. Okay. Thank you very much for that question. But as I was saying, since this energy intensity is supposed to be at this level, it's considered quite infeasible. And even with the IEA Sustainable Development scenario, where they explore every feasible sort of energy efficiency projects being deployed in that scenario, they arrive at the conclusion that energy intensity only improves by 3.6% year on year from 2018 to 2040. Again, this is quite ambitious as well, and therefore it looks almost infeasible to be able to achieve this. And like I highlighted before, our reliance increases every year that we go without that significant CO2 reduction.
Thank you very much indeed. I'm trying to sort of find the question that arrived, but basically it was very detailed about, and somebody who's clearly following the CCS landscape very closely, talking about the fact that we've got 19 projects operating, and as outlined, I think in our status report, the 4 projects under construction and more than 20 in various different phases of the pipeline. But the question is related to the COVID pandemic and the ongoing economic circumstances. So we've been asked if we're seeing a slowdown in the progress of these projects, and or are we seeing economies, governments kind of putting CCS into their economic recovery plans?
Shall I call that, Nabila? Yeah. Yeah. So I guess in terms of the slowdown, I think I guess we're not seeing announcements in terms of those facilities that are currently in the pipeline. Of course, industry will be facing many other challenges at the moment, and with CCS being a large-scale infrastructure project, it faces the challenges of all large capital projects in terms of sort of maintaining financing through these difficult times. So I think it's certainly a challenge. I think on the flip side, as you say, Lauren, you've got the opportunity. So there's certainly been a few governments who have either announced or are considering CCS, and as part of a broader package, I guess, focus on transitioning us to a sort of net zero pathway, investing in large-scale infrastructure, which can provide those jobs that we mentioned earlier. So I think it's definitely being kind of considered, but I think it's part of a wider trend rather than a sort of specific CCS trend that we're seeing.
Okay, thank you. A number of questions and actually I have to say comments about CCS and power, particular, renewables, and also some questions around batteries. Don't they kind of provide a better solution? Don't they provide the service? And renewable costs have come down, etc., etc. Should we still think about CCS and power? I know you touched upon it, Nabila, but also if you could talk about the battery point potentially.
Thanks for that question. So again, just highlighting what we said before about benefits of CCS being dispatchability, as well as the ability to provide ancillary services, which are essential to maintain the reliability and stability of the grid. And we have to be sort of taken into context with regard to renewables, because their intermittency makes them unable to provide these essential services. If you, for example, look at the fact that where CCS is able to complement the deployment of greater renewables, especially because of this problem of intermittency. And of course, within this context, batteries can and do play a valuable role in managing that short-term intermittency and storage of that generated power as well. However, we also have to look at the fact that batteries need to be able to provide backup for a period of days or weeks even, and it will be required if a grid contains more dispatchable generation capacity, if that's what we're trying to do with only renewables and without CCS. And if you take into context the fact that the world's largest lithium-ion battery, which is installed in South Australia at the moment, it has the capacity only to supply 100 megawatts of electricity to the grid at about 75 minutes at full discharge. And so again, those problems of that intermittency can be again, and also these limitations of battery storage, they can be complemented by CCS equipped power plants as well, along with renewables as well, and these battery options. And it's more of a question for an electrical engineer at this point, but studies have shown that if you take it from a whole systems cost perspective as well, CCS has played a valuable role in basically complementing these other low carbon sources of generation. Hope that answers the question.
I think that's a comprehensive answer, Nabila. Thank you. Alex, you discussed hydrogen. Some comments and questions about what we hear, I think, quite often in Europe, actually, green versus blue hydrogen. Doesn't it make sense to go green? And some questions around how long do we expect kind of blue hydrogen to be cost competitive, given the cost of electrolyzers coming down, etc. Could you just talk a little bit about it? I know, again, you touched upon it, but there have been a number of sort of comments on this.
Yeah, and I think it's interesting when you kind of look at it from a global perspective and the different regions, and there's sort of different perspectives in terms of the role and the balance of green versus blue hydrogen. I mean, ultimately, production of low carbon hydrogen, regardless of the colour, is really important for establishing the hydrogen infrastructure and the markets. So I think we need to pursue all options. There'll be some regions where perhaps the balance is more in favour of blue hydrogen than green hydrogen, others where it'll be the other way around. And so, that's something which would be considered, I guess, on that kind of more sort of country level basis. But I think, from the work that we've done, there's clearly a role for and an important role for blue hydrogen in terms of, at the moment, being cost effective, the most cost effective option, being the place where you can achieve that scale quickly, and therefore help to establish the hydrogen market. And then I guess, if you were to support both technologies, ultimately what happens in the future is the one that's most kind of cost effective in that particular region will kind of come out as the predominant technology. And I think, supporting both all forms of hydrogen production to scale up that low carbon production, I think should be the near-term priority.
Thank you. There have been a number of kind of quite detailed questions I jotted down about storage options, risks, etc., about decommissioning that you mentioned, and a number of others. And with that, I would actually like to bring this Q&A session to a close. As I said, we've collated the questions, and particularly with these more detailed questions, we'll try to get back to you with specific answers in the coming days. I would like to, Alex, if I can have the next slide, I would like to point out, though, the report that we've been discussing, the Value of CCS, is available on our website to download. It's under the resources section. We also have our global status of CCS report. It's basically anything and everything you may want to know about CCS, including the database, a summary of the database of projects existing under construction and under development. So that's, again, also available on our website to download. Finally, we are continuing with our program of CCS talks, the webinar series, and the next webinar will be on the EU Green Deal and CCS. We'll have a fireside chat with DG Klima's director, Mr. Arthur Metzger, and that's again next week, 19th of May. You can follow us on social media with the relevant hashtags that I've listed down there. And if you have further questions, suggestions about webinars, or would like to learn more about our consulting and our client offerings, please get in touch with us through the emails that have been listed. On that note, thank you very much again for joining us today, and we hope to see you in our next webinar. Have a good day.